Did you know that scientists can take one element and turn it into another by taking an atom and slamming protons and neutrons into it? Yeah, it's true. This is called nuclear transformation, which is also sometimes known as nuclear transmutation. And this is a big deal because for thousands of years people have been trying to turn one element into another, right? Like the alchemists were all about doing this. They wanted to fixate on the idea of turning lead into gold. And they thought oh, if I boil the lead in a big pot and add some lizard's eyes and mouse tails and say the right spells, maybe I can turn lead into gold. Well, that's not easy because lead and gold are totally different elements. It's not just like melting water or something like that. So to change one element into another, you've got to change the number of protons that are in its nucleus. You've already seen one way that one element can turn into another, and that's in radioactive decay, where you have something like alpha decay or beta decay or positron decay that changes the number of protons and neutrons in the nucleus. But decay processes just happen by themselves in nature. And in the lab, scientists are able to make this change happen by taking an atom and slamming these protons and neutrons into it. So we can define nuclear transformation or mutation, changing an atom into a different element by slamming protons and neutrons into it. So that's what we're going to talk about in this video. We're going to talk about nuclear transformation. We're going to talk about how to write equations for it. And then we're going to see how nuclear transmutation can be used in the lab to make elements that we can't find in nature. These are called the transuranium elements, and all of them have atomic numbers above 92. So let's get started and look at a diagram of what nuclear transmutation would look like if we could zoom in to an atom and be able to see all the protons and neutrons that make it up as well as the electrons. So, okay, so here is an atom of nitrogen-14, okay? And over here I have an alpha particle, which is made of 2 protons and 2 neutrons. My little red dots here represent protons, the blue dots represent neutrons. So if we want to do some nuclear transformation, some nuclear transmutation, we take this alpha particle and bam, we'd slam it into the nucleus of this atom. And if we were lucky, it would stick. And the protons and neutrons that are in this alpha particle would end up stuck in here in the nucleus. Okay? So I want to write this as an actual nuclear equation instead of just using the diagram. So here's what I do. I'd write it as 4,2 alpha plus 14,7 nitrogen. Okay, that's no big deal. But now let's look at what we get out of this. When you do a nuclear transformation reaction, you usually end up with a new element, and then you get a little bit of change. And by change I mean a couple protons or a couple neutrons extra get kicked out in the end. So when we do this reaction, here's what we end up getting. We get a new atom, and it's an atom of oxygen-17 here, okay? When I'm doing a nuclear transformation reaction like this, I don't make any new neutrons, I don't make any new protons, which means that the number of neutrons and protons I have on one side of the equation is going to balance the number of neutrons and protons that I have on the other side of the equation. So when I'm writing these, I find that it helps to keep track of the numbers that I have of both. Okay? So I'll do the number of neutrons and protons together is the mass number up here. As if you remember, as I'm writing these isotope notation symbols, the number that I have up here is a mass number, which is a number of protons and neutrons. So there are 4 protons and neutrons together in the alpha particle, and there are 14 protons and neutrons together in this atom of nitrogen. So that means that altogether I have 19 neutrons and protons here. How many protons do I have? Well, I have 2 in the alpha particle, and then I have 7 in the nitrogen here. So that means in total I'm going to have 9. The same is going to be true over on this side of the equation. 18 neutrons and protons, and 9 protons. So I get this new atom of oxygen, and I said that I usually get a little bit of change when I do this kind of equation. What's the change that I get here? Well, I need to, since there are 9 protons on this side of the equation, there need to be 9 protons on this side of the equation as well. But in oxygen, I only have 8 protons. So that means that I have to have an additional proton on this side of the equation. You can write that in like this. This is the symbol for proton. You get a P, and then there's 1 because it has 1 proton in it, and the protons plus neutrons equals 1 as well. Now these guys add up, and these guys add up. So what happens here is that I get the alpha particle slamming into the nitrogen, and that then gives me these two things. I get an atom of oxygen, and I get that because I increase the number of protons, but only one of the protons stays in this new atom, and the other one comes shooting out. So I've got it here. So I get 2 separate things. I get a new atom of oxygen, and then I get this additional extra proton, which I write right here. This is what I keep referring to as like the change, the little bit of extra that I get out. And I can figure out what it is by seeing how the number of protons and neutrons are going to add up on both sides of the equation. Let's do another example. Okay, in this example, I'm going to start with an atom of aluminum 27, and as before, I'm going to take an alpha particle, 2 protons and 2 neutrons, and slam that alpha particle into this aluminum. You know what, there's a fancy word for slamming, and it's a good word to know. It's called bombard. And so a lot of times when we're talking about slamming alpha particles or protons and neutrons into an element, I'll use the term bombard, and you'll find that in textbooks and stuff like that, because it sounds a little bit smarter, it sounds a little bit more technical than having to say slam or smash. So bombard, you might also notice in like daily life. People say bombard a lot. Well, maybe not a lot, but you can find it used in daily life. Bombard technically means like to bomb something, right? To like throw bombs at it. But often people will say that they got bombarded by questions, they got bombarded by people asking for their autographs. So it's like when you have all sorts of things coming at you is what bombard means. So anyway, so we take this atom of aluminum and we bombard it with the alpha particles. So here's the kind of question that you might get like on a test or in some practice problems or something. We get some new element, and then as change, the thing that we also end up getting is 1 neutron. So my question to you is, what's this element? What's this other element that we're going to end up getting? How do we figure it out? What I like to do is I like to add up the protons and neutrons on one side, the protons and neutrons on the other. Okay, so let me have the mass numbers, the total neutrons and protons together. 27 plus 4 is going to be 31. And then the total protons are going to be 15. That's what I have on this side, and it has to be the same on this side. Okay? So we know that we get 1 neutron out of this equation. How many protons do we have to have? Well, we want to have 15 protons on this side of the equation, and since there are no protons in the neutron here, that means that all of the protons need to be in whatever else I get after this transformation reaction. How many neutrons? Well, the neutrons and protons have to add up to 31, because 27 plus 4 is 31. I've got 1 over here, which means that if I have 30 neutrons and protons in this mystery element here, that 30 plus the 1 over here in the neutron is going to add up to 31. Okay? So these are the numbers. These add up, they equal each other on both sides. And now all I've got to do is figure out what letter to write here. I do that by looking at 15, which is the atomic number. So I go to the periodic table and I find out which of my elements has an atomic number of 15. Turns out it's phosphorus here. So I put a big P, and what I've written is the equation for bombarding aluminum with alpha particles. It gives me a new atom of phosphorus. It changed the aluminum into phosphorus. And then I also got a neutron spitting out as well. So here's the equation for this alpha bombardment. Now, it's not always alpha particles that we slam into things. And in fact, alpha particles are kind of hard to slam into atoms because alpha particles have those 2 protons, which means that they have a positive charge of +2. The neutrons, they don't have any charge, so they don't contribute in that way. But so we got this nucleus of an atom. and it has a bunch of protons in it. So it's positively charged. And then we have this alpha particle with 2 positively charged protons coming at it. And so it is actually a difficult thing to do because they both have positive charge. And what do you know about positive charges or like charges? Like charges want to repel, right? So in order to slam a positively charged alpha particle into a positively charged nucleus of an atom, you really got to speed up that alpha particle. You got to get it going super fast, like almost close to the speed of light sometimes, in order to be able to slam it into that atom so it will stick. It's a lot easier, actually, to take neutrons and slam those into the nucleus of an atom. You know, I should start using the smart word. It's a lot easier to bombard a nucleus with neutrons. And why is that? It's because neutrons don't have a positive charge, so they're not going to be repelled by the nucleus. It's like no big deal, you know, they can go and just smash into it. So we have to use these really complex machines called particle accelerators in order to speed up things like alpha particles fast enough that they can slam into a nucleus. But it's not as hard to slam a neutron in. Okay, so that's, I think, an important thing to remember. I now want to write a decay equation for another type of nuclear transformation. Here's how it goes. I start out with an atom of lithium-6, and I meant to do this, and I add some mystery thing to it here. And what I end up getting out is hydrogen-3 as well as an alpha particle. Sometimes alpha particles can come out. They don't necessarily have to go in. So, what is the mystery thing that I added to the lithium? Let's add up the protons and neutrons on both sides of the equation. Neutrons and protons on this side, I have 3 plus 4, so I got 7, and my protons add up to 3. We want it to be the same on this side. So I already have my 3 protons in the lithium. Got 3 protons on this side, so whatever I'm adding, it's not going to have any protons in it because I already have 3 here. I want to have 6 protons and neutrons on this side of the equation, but I only have 6 protons and neutrons together in lithium. So what I'm going to want to add is 1 neutron and no protons. And so the symbol for neutron is 1, 0 with an N here. This is an example of neutron bombardment, right? As I said, we don't always have to bombard things with alpha particles. We can use neutrons, we can use a variety, we can use more than 1 neutron and so forth. So that's this equation for neutron bombardment here.